Hi Jyoti, we'll start the session in a few minutes. We'll wait for others to join in.
Okay, thank you.
Good morning, sir.
Good morning, Vasu Babu.
Thank you very much.
We'll start the session in a few minutes. We'll
Yes,
wait
sir.
for we'll wait for the others to join.
Okay, sir. I will. Sir, please consider my request. I am already saying my
Hello. Yeah, I your voice is not completely clear. Maybe you can
Sir,
just type out your question.
okay, sir. Please consider my request, sir. Previously, I requested for some other things it is very difficult to, as a engineering graduate to understand the assignment is very difficult to like this. Sir.
Yeah, I have passed on your message, Vasu Babu, to
Sir.
to the instructor and to the TA who is setting the assignments.
Yes, sir.
Uh, so, uh, so in your final exam, if you are taking up the exam, you can expect questions at this level, at the level of the assignments. So,
Of the level
to
of
train,
assessment.
yeah. So to train yourself at that level, it is better that you practice these because it whatever we are asking in the assignment directly from the videos. Uh,
Yes, sir. As a engineering graduate, it is very difficult to understand the science studies. In there, I am asking you.
you can the what will happen is if you skip any video in between, then it will be hard for you to if you start watching, like, for example, there's a link between each video.
Yes, sir. Yes, sir. At least please consider my request, sir. Thank you for
Yeah,
your
yeah,
acceptance, sir.
sure.
Thank you very much, sir.
So we'll start the session now. I'll just share my slides. So I hope my slide is visible.
Yes, sir. Yes, sir.
Okay. Okay. So I'll just start explaining. So the format that we'll follow is similar to the previous weeks. I'll first give you guys 1 minute or 30 seconds to go through the question, and then maybe you can type out your answer in the chat box, and then I'll explain. I'll go through the question and explain the corresponding concept. Uh, so you can just read this question and type out your answer in the chat box. So this is continuation from week two. The concept is from week two. Uh, Last week I had skipped these two. I said that I will do it in this week, and we also have a few questions left from week two. So we'll finish those, and then we'll go move on to week three. Uh, so I'll just set an alarm for 30 seconds, timer for 30 seconds. Okay, let's see if anybody has responded. Okay, see, higher no overlap exists between the uh, actin filaments. Okay, okay, so I'll go to the question. At short sarcomere length, the force produced is dash because dash. Uh, higher, comma more active sites along actin is available for binding with myosin. Uh, so let us recall what happens. Let me just go to this slide. So this is the relationship between the sarcomere length and the force, as you if you recall from the class. So you can see here what is happening. At a shorter sarcomere length, the force that is being produced is less, and that is because the actin binding sites, the actin filaments is overlapping. So the thin filament or the actin filaments are overlapping. And here in this case, when the sarcomere length is too big, then what is happening is there is no overlap between the actin filament and the myosin filament. So again, cross bridges cannot be formed. Whereas when the sarcomere length is small, actin filaments are overlapping. Hence, again, cross bridges cannot be formed because this overlap between actin filaments is blocking the binding sites, and hence the myosin heads cannot attach to the actin binding sites. So the answer is lower. We can see this the sarcomere length when it is lower. Uh, in this case, the force is also lower, and also the reason is so we here itself by looking at the graph we can eliminate two options. So it is not higher. So A and C is gone. Between B and D, we need to choose. The answer is actin filaments overlap and hence myosin cannot easily attach to actin. So this is the correct option. Here, actin filaments are too far from the myosin head. This is the case when the sarcomere length is bigger. Okay, and this is for B case. So the answer is B. So we'll move on to the next question. As shortening velocity increases, muscle force production decreases because A. There is a progressive decrease in the number of attached cross bridges. B. There is overlap of actin filaments resulting in lesser active binding sites. C. Both A and B. D. None of the above. So again, I'll give you 30 seconds. You can type out your answer in the chat box. Okay, let's see what the response is. Okay, B, C, and B. Okay, let's go through this. So actually the answer is A. Okay, B. The answer is not B because that is the case when the sarcomere length is bigger and then there is no overlap between the actin, which is the thin filament, and myosin, which is the thick filament. In that case, the force is less, but that is not linked with shortening velocity increase. When the velocity increases, the time required for the cross bridges to form is less, and hence there is a progressive decrease in the number of attached cross bridges. So the answer is A. Uh, Another thing that I wanted to mention was the book for this for these topics. You can refer to the book Candle and Schwartz. Uh, if you want further details, if you want to go in more depth, you can refer Candle and Schwartz. Okay. Select all correct statements. So this is going to be slightly tough. I'll give you around 2 minutes, 2 to 3 minutes to answer this, and then we'll discuss each and every option. You have another minute left. Okay, let's discuss. Let's see what the responses are. Okay, F comma G, F G H. Okay. Okay, so these are the two responses. So let us go through uh, this question once again. So neurotransmitters are only excitatory and never inhibitory. This is false because we know that neurotransmitters can also cause an excitation as well as an inhibition. For example, GABA, uh, which causes an inhibition, or hyperpolarization. So A is not the correct answer statement. Neurotransmitters are chemical transmitters and communication is bidirectional. Yes, neurotransmitter are chemical transmitters, but communication is not bidirectional, it's unidirectional. So this is something that you need to recall, that sir has mentioned it in one of the videos, that these are unidirectional, not bidirectional. However, in electrical synapses, the communication can be bidirectional because the mode of communication is through ions. Let us recall that in electrical synapses, the communication happens through ions and it's very fast, and it is bidirectional. But whereas in chemical synapses, uh, the communication happens through chemicals such as through neurotransmitters, and it's not bidirectional, it's only unidirectional. C, acetylcholine is a neurotransmitter and amino acids are not neurotransmitters. This is false because we know that GABA is an amino acid and that also happens to be a neurotransmitter. End plate potential is an action potential. This is also false. End plate potentials can sum up to reach threshold, and then an action potential can be generated, or end plate potentials uh, can cause an action potential in the neighboring regions in the within the muscle fiber, but it is not necessary that an end plate potential is an action potential. It can sum up to become reach threshold and cause an action potential. Agent of communication in an electrical synapse is ion, and the communication is unidirectional. Again, this is the wrong part. It is bidirectional in an electrical synapse. Smallest possible change in membrane potential of the motor end plate is called as miniature end plate potential. This is correct. This is correct. So let's write this down. F. So I think you guys got this part correct. F. So let us recall how a miniature end plate potential is caused. Uh, the smallest possible change can be due to one vesicle of acetylcholine. So in the neuromuscular junction, we know that uh, the neurotransmitters are released via vesicles. So they are packed in vesicles in the presynaptic membrane, and uh, these vesicles are released into the synapse. So the end plate potential caused due to one vesicle, the acetylcholine in one vesicle, is called miniature end plate potential, and it also happens to be the smallest due to one vesicle. The change in the end plate potential due to one vesicle, the ACH in one vesicle, is also the smallest change. Then let us look at G. Choline acetyl transferase converts acetylcholine into choline and acetate. So this is not correct. Let us recall what happens. Choline acetyl transferase is responsible for, so this is CHAT, CHAT, choline acetyl transferase. So in the presynaptic, uh, uh, so this is the neuromuscular junction, and we have the muscle fiber here. Uh, so what happens is we have vesicles in the presynaptic membrane, in the presynaptic. Uh, so this is an axon, and we know that an action potential travels to the axonal end bulb. Uh, and what happens is we have acetylcholine which is packed into vesicles. So that is done uh, that is mediated by choline acetyl transferase. Uh, and we have another chemical here, acetylcholine esterase, which which converts acetylcholine, which breaks down acetylcholine into choline and acetate. So it is choline acet. If it was acetylcholine esterase, then this would have been the correct option. So this is false. This is not correct. And H, triggering of ligand-gated sodium channels occurs when acetylcholine reaches the nicotinic cholinergic receptors on the postsynaptic membrane. So this is correct. We know that acetylcholine is released, and via diffusion, it reaches these ligand-gated sodium channels called nicotinic cholinergic receptors. So it's like a lock and key mechanism. The lock is the nicotinic cholinergic receptor, and the key is the acetylcholine chemical. And when it attaches to this receptor, it opens up and it allows sodium to enter, causing a depolarization in this particular region. So the answer is F and G, F and H. uh, so let me just erase this. So the answer is F comma H. Okay, so let us go to the next question. Again, this is a slightly tough question. So you can go through this, and I'll set an alarm for 2 minutes, a timer for 2 minutes, and then we'll discuss this question. Okay, let's discuss. Let's see what the responses are. Uh, do you need some more time to go through the question? D and D. Okay. Okay. So I'll just type it out here. I'll write it here. D and D. Let's see if there's any other response. Okay. Okay. I'll discuss these questions now. In the rest state, actin is completely wrapped and covered by troponin. So let us recall that the thin filament is composed of actin, troponin, and tropomyosin, and the myosin binding sites are covered by uh, tropomyosin, not troponin. So this is the wrong option. This should be tropomyosin. B, when calcium is released in large quantities from the sarcoplasmic reticulum, tropomyosin reacts, causing troponin to expose the active binding sites of actin. Uh, so again, this is wrong because uh, when what happens is calcium reacts with troponin, and then troponin is attached to tropomyosin. So when there's an influx of calcium into the ICF of the muscle fiber, uh, calcium attaches to calcium attaches to troponin, and troponin undergoes a conformational change. And since troponin is attached to tropomyosin, it moves when it undergoes a conformational change. It moves tropomyosin, and this leads to exposure of the myosin binding sites on the actin. So this B is the wrong answer. The answer should be troponin reacts, causing tropomyosin to expose the active binding sites of actin. Myosin head is in high energy form when ATP is hydrolyzed to ADP plus PI. This is the correct statement. So if you recall the sliding filament theory, uh, one of the steps in the sliding filament theory is that ATP, which is attached to the myosin head, gets hydrolyzed to ADP plus PI, and in this particular state, uh, the myosin head is in the high energy state. So this is the correct answer. C. In rest state, actin is completely wrapped and covered by tropomyosin. So this is correct. So I think a better way to put this would be, uh, we can remove this word completely. We can just say actin is wrapped and covered by tropomyosin. Okay, so C and D is correct. When calcium is released in large quantities from the sarcoplasmic reticulum, troponin reacts, causing tropomyosin to expose the active binding site. So this is correct. We just discussed this. This is the opposite of B. Uh, so I just explained the sequence, and this is the troponin undergoes a conformational change, causing tropomyosin to expose the active binding sites of actin. Then F, thick filaments are called as myosin and thin filaments are called as sarcomeres. This is wrong. Let us recall that thin filaments are called as actin. So you can remember the word actin rhymes with thin. So that is a way to remember this. And sarcomere is the content between two Z discs. That is sarcomere. That is the smallest functional unit of a muscle. So a sarcomere contains both actin, thin and thick filaments. So this is false. This is not the correct answer. The thin filaments are held together on the Z disc by a strong contractile protein called titin. This is wrong because the thick filaments that is held together on the Z disc by titin. So the answer should be C, D, and E. I think two options were correct. Okay, moving on to the next question. Let's see if there are any responses. Okay. Okay, so we'll discuss this question. Which of the following statements is true in the context of synapses? Again, I'll give 2 minutes to answer this question, and then I'll go through each of these options. Okay, so let's see if there's any response. BENG. Okay. Okay, so let us go through this. Which of the following statements is true in the context of synapses? So, axonal terminals always synapses with dendrites of the next neuron. This is not true. It can synapse with many other parts of a neuron as well. Uh, so, this is not the correct statement. The neurotransmitters are stored in vesicles within the axonal terminals. This is correct. Proteins called synaptotagmins, which are attached to these vesicles, are sensitive to the presence of Na plus ions. This is false. Synaptotagmins, which are attached to vesicles, are sensitive to calcium, not sodium ions. So this is the wrong statement. Adenosine, histamine, acetylcholine, dopamine, and GABA are some examples of neurotransmitters. This is correct. So D is also a correct statement. Snare proteins facilitate the docking of vesicles to the membrane uh, of synaptic end bulb. So this is correct. Snare proteins, which are syntaxin and synaptobrevin, facilitate this docking of vesicles onto the synaptic end bulb. So this is correct. In the absence of snare proteins, the neurotransmitters can still be effectively released. Uh, no, this is not true. We need the snare proteins, otherwise there won't be any docking happening, and there won't be any exocytosis, which is the process which leads to the release of neurotransmitters into the synapse. So that is wrong. Uh, the release neurotransmitters cross the postsynaptic membrane. No, they cross across the synapse and attach to uh, uh, they attach to sensors on the postsynaptic membrane. They don't cross the postsynaptic membrane. So this is false. Opening of the ligand-gated sodium channels cause the formation of uh, end plate potential at the postsynaptic membrane. Yes, this is correct. So let us recall what happens. The neurotransmitter attaches to the nicotinic cholinergic receptor in the postsynaptic membrane, which is a ligand-gated sodium channel. And once the ligand-gated sodium channel opens up, there's an influx of sodium, causing a depolarization or an end plate potential in the postsynaptic membrane. So the answer is B, D, E, and H. So this is the answer. So I think B and D where you got B and D correct. Okay. So moving on to the final question for week 2. Which of the following are the right steps in excitation contraction coupling? So let's see. Yeah. So I'll again give 2 minutes and then we'll discuss this. Another 15 seconds. Okay, let's see if there are any responses. Okay, do you need more time? Okay, B and D. Okay, let me write it down here. B, comma D. So let us go through this. Which of the following are the right steps in the excitation contraction coupling? When neurotransmitters are released into the neuromuscular junction, a wave of depolarization is transmitted along the length of the muscle fiber. So this is correct, right? Essentially, what happens is when the neurotransmitter is released, there is a end plate potential caused, and this end plate potential uh, can sum up to cause an action potential which can travel along the length of the muscle fiber. So this is correct. Extensions slash invaginations of the sarcolemma called T tubules are carried a depolarization wave deep into the muscle fiber. Again, this is correct. Dihydropyridine receptors in is a ligand gated sodium channel present on the T tubule. This is false because it's not ligand gated. It's actually voltage gated. It's a voltage gated channel. So this is false. Opening of DHPR receptors in the T tubule also causes the opening of ryanodine receptors in the sarcoplasmic reticulum. This is correct. So, if you recall, the process by which this happens, opening of DHPR causes the opening of ryanodine receptor through food processes, FOT, food processes. Uh, okay, so let us go to the next option. The sarcoplasmic reticulum, which is the storage of sodium ions, releases the contents into the ECF. This is false. It releases calcium ions, not sodium ions. So this is false. So the calcium spark in the and it is not into the ECF, it is into the ICF of the muscle fiber. The calcium spark in the ICF causes interaction of actin and myosin filaments causing contraction. Yes, this is correct. The calcium ions passively diffuse into SR along the into the sarcoplasmic reticulum along the concentration gradient without the expense of energy. This is false. We know that a calcium pump actually pumps the calcium ions, which is in the ICF of the muscle fiber, into the sarcoplasmic reticulum. So this is false. The contraction continues until calcium is actively pumped back into the sarcoplasmic reticulum. This is correct. So the correct options are A, B, D, F, and H. This is a slightly complicated problem where there are multiple correct answers. Okay, so we are done with week 2's questions. Let us move on to week 3. Uh, so Tony is carrying a box of training materials directly in front of him as he is on way to set up a seminar room prior to the start of a presentation. While he is walking, his biceps remain in a fixed position and are not being raised or lowered. This is an example of A. Involuntary contractions, B. Eccentric contractions, C. Isotonic contractions, or D. Isometric contractions. So I'll give you guys 30 seconds to answer this, and then I'll discuss this in detail. So you can see that the pattern of questions that I'm discussing. So the initial questions are simpler, and then towards the end of a particular week, for example, you can see in this particular week, in week 2, the questions become progressively complicated, but the initial questions were simpler. Similarly for week 3 as well, we'll discuss simpler questions first, and then towards the end we'll discuss more complicated questions. Okay. Okay, so let us discuss this. Let's see what are the responses. You can respond if you are able to. You can also have a guess. It need not be correct, and then we can discuss each and every option. Okay. Since there is no response, I'll discuss the question. So, let us recall what happens. Since the biceps remain in a fixed position and are not being raised, this means that the muscle tendon unit length, muscle plus tendon unit length is constant, right? So this is an example of isometric, right? Isometric contraction. This means that since the muscle tendon unit length remains constant, the contraction that is happening in the muscle is isometric because there's no change in the muscle tendon unit length. If there is a change in the muscle tendon unit length, but the force that is being exerted is constant, then it is a case of isotonic contraction. And eccentric contraction are those contractions in which uh, the muscle length is increasing. Is there anybody? Okay, I think somebody joined left and joined back. Uh, so yeah, eccentric contractions are those contractions when there is a lengthening of the muscle tendon unit length. So for example, if the weight that you're trying to carry is heavier, or if for example when you're holding a dumbbell and then you're doing this flexion extension, during the extension phase, what happens is the muscle is lengthening. There's a contraction, but there is a lengthening of the muscle that is happening, of the biceps. So that is a case of eccentric contraction. And then involuntary contraction are those contractions in which we don't have any control. Uh, so that is not the correct option. So the answer is D. Muscle contractions that result in muscle shortening are known as. So you can take a guess. I'll give 30 seconds. Okay. Let us discuss this. Let's see what are the responses. D. Okay. Okay. So let us now go through each of this. So like I discussed this now, eccentric contractions lead to muscle lengthening, right? So this is not the correct answer. Concentric contraction on the other hand leads to muscle shortening. So this is the correct answer. And we have two other options: slow twitch contractions and fast twitch contractions. So let us, if you recall, a motor unit is what is a motor unit? A motor unit is motor neuron and all the muscle fibers that it innervates. So that is that unit is called a motor unit. So if a motor, there are different kinds of motor units. So if a particular motor neuron uh, innervates many muscle fibers, then that's a big, the innervation number is higher, hence the motor unit size is more bigger. Whereas we have motor units whose innervation number is smaller, hence we call those as smaller motor units. So these motor units have various different properties. So some motor units uh, the contraction time, for example, this is a particular uh, twitch contraction. So a twitch contraction is the contraction, the force caused due to one particular motor unit. Okay, due to an action, when one particular motor unit fires, then the force that is created is called a twitch contraction. So this the force. So this is the force axis. Let's say this is the force axis, and this is the time axis. So in a fast twitch contraction, when a twitch is caused due to a fast a particular motor unit which is fast, then the force that is generated is higher. The magnitude of force that is generated is higher, and it also rises and falls down quickly. So for a shorter duration. Similarly, for a slow twitch, the duration is longer, but the force that is produced is smaller. So these two are not the correct options. Because these two are different concepts altogether. Let me go on to the next question. A marathon runner will have greater percentage of dash muscle fibers. Fast twitch, slow twitch, eccentric, intermediate. So again, let us. I'll give you 30 seconds, and then we'll have a discussion about this. So marathon runner will have a greater percentage of fast. Let me see what are the responses here. A, okay. Okay, so let us discuss this. Okay. So Bosobobo has responded A. Yes, actually that's correct. So let us discuss each of these options. Fast twitch is the correct option. Slow twitch is the wrong option. Eccentric is a different concept itself. It's lengthening of muscle. It has nothing to do with what we're discussing here in this context. So this is wrong. And intermediate is also wrong. So let us discuss uh, why this is the case. Let me just drag this slide here. So you can see here that there are different types of muscle fibers: type 1, type 2a, type 2ab, type 2b. Okay, and you can see that the fast muscle fiber is highly fatigable, but it produces more force, right? Fast muscle fibers produce more force. So this is type 2b muscle fibers. They are fast, and they are highly fatigable, but they produce more force. So uh, let me take this back. So so sorry, this is a marathon runner, right? Let, so what I'm discussing is for a sprinter. So this is wrong. It's slow twitch. So uh, let me bring this back here. I by mistake I thought this as a I mistook this as a sprinter. So type 1 is slow. It is a slow muscle fiber. And it is extremely fatigue resistant. So this is required for walking, right? Uh, so what we need is a marathon runner needs slow twitch fibers because they are more fatigue resistant, right? A marathon runner does not need an explosive force production. So, for example, a runner like Usain Bolt, who is a sprinter, he needs an explosive. He needs to generate an explosive burst of force to run the sprint. So he will need fast twitch fibers which generate more force, but they are extremely fatigable. However, a marathon runner needs does not need to generate an explosive burst of force, but instead the marathon runner, for example, Mo Farah, uh, he needs he does not want to become tired fast. So in that case, he will use slow twitch. He will do exercises that generate muscle fibers, which are slow twitch muscle fibers, which are uh, which don't get fatigued easily. So this is the correct answer, switch. Also, we can have intermediate muscle fibers that are get fatigue, don't that are still fatigue resistant, but can still be fast. So this option is slightly ambiguous, but the safe option is slow twitch. This is the correct option. So we'll go on to the next question. Which of the following angles of pennate muscle fiber transmit maximum force through the tendon? A 90, B 10, C 45, and D 30 degrees. So I'll just put a timer for 30 seconds. Okay, let's see what the answers are, responses are. C. Okay, both have responded C. Which of the following transmit maximum force through the tendon? Okay. Okay, so let us recall how this works. Let us consider an example of a unipennate muscle. So this is the muscle tendon, and then we have muscle fibers here, right? We have muscle fibers here. Uh, so this is the force that is generated. The muscle contracts, and the force is along the muscle fiber contracts, and the force is along this direction. And this is the pennation angle, right? Theta. So the force F here, the component. So we can split this F into two components, horizontal and a vertical component. So this component and this component. So this is the pennation angle. So this is F cos theta, and this is F sin theta, right? We can split this particular force into two components. So F cos theta is the force that is actually transmitted, right? So these muscle fibers uh, create a force F, but only F cos theta is actually transmitted through the tendon. Only this component is transmitted through the tendon. So if you recall, uh, theta when it is small, when it is 90 degrees, cos 90 is 0, but when you keep decreasing theta, then what happens is its value increases, right? Cos theta value increases, so it increases from 0 to 1. Okay, so 90 to 0 degree. So when theta changes from 90 to 0 degrees, cos theta changes from 0 to 1. So here we want the least angle, right? So the least angle is 10 degrees. So the answer should be B. So in that case, the maximum amount of force will be transmitted through the tendon. I just want to go back to the previous question. This is slightly ambiguous. The correct option should have been either type 1, type 2A, type 2AB, type 2B. These should have been the options, because a marathon runner can also use type 2A muscle fibers, which is also fatigue resistant, but it is also fast, right? So uh, you can ignore the this particular question, this particular explanation. So marathon runner can use type 2A as well as type 1 fibers. Whereas because these are fatigue resistant, you can see extremely fatigue resistant and fatigue resistant. And we can also argue that the marathon runner can use this particular type 2AB, because you can see it is used in jogging, right? So again, this is fast. These are fast fibers. But a sprinter is one who uses this type 2B, which is extremely fast and highly fatigable. This produces the most force, uh, but it gets fatigued very quickly, right? So the question could have been framed better. Uh, so we'll stop the discussion here now. It's 6:02. We'll stop the discussion here, and we'll discuss the remaining questions in the next class. So there are totally 18 questions in week, 17 questions in week 3. We'll continue this discussion in the next class. Let me just save this. So if you have any further questions, you can let me know. Thank you.
Thank you, sir. Thank you, sir.
Thank you, Basu, and thank you, Jyoti, for joining in. Kindly join in next week as well. So we'll continue the discussion next week. Okay, bye.
Bye, sir.